This time, uh, I have got my good friend Mahesh from Tiny Prism Labs, who was my batchmate in engineering, and also he has worked as project assistant at ASC, Department of um, Atmosphere and Oceanic Sciences, I think. Then after that, he did his ME from Manipal and also worked at ARM for a brief time, and is running Tiny Prism Labs right now, which is into building products and solutions in AML and embedded systems. Uh, so Mahesh will be presenting on uh, different aspects, his learning from building a medical device and approaches to electronic uh, product development. And we'll have a brief discussion on the same, and we'll have a Q&A after that.
I'll share briefly on the device that we tried building, a medical device to be very specific. And then I will walk through the kind of challenges and the learning that we have gone through, and things that I would rather say for an early startup or a founder who is not from a background of electronics, who would try to build what could be certain things that he'll have to be familiar with, or have to at least do some homework so that you can plan well. So I think 2 years back, 2.5 years roughly, is when we started Tiny Prism Labs, and we had the task of building a device for a disorder called dysphagia. And dysphagia is basically a swallowing disorder where somebody who's trying to have a sip of water or a food will not be able to have it at ease as we are able to have, because the food, instead of going into the food pipe, will go into the windpipe, and then the person who is having dysphagia or is likely to have dysphagia have to struggle to have every meal. Now, a disorder like this, if detected early, has therapy and treatments to come out of it. Otherwise, they'll have to go through complex surgeries in order to get recovered. And the need for such a disorder being identified non-invasively was also the task. Because the current day diagnosis for such a device or such a process was invasive, where they would be asked to swallow barium liquid, and they swallowing a liquid would be, X-ray. Through X-ray they would take a reading called as video fluoroscopy, and that visualized data of swallowing, doctor would be able to analyze and tell at what degree of challenge they would have. So now, this being the problem, when we started, we said, okay, fine. Back then we were new to the medical world, and we just built a rudimentary working module, and then what we could get working through a belt wrapped around this particular device, which Sumanth and Stelna Designs designed the casing for me very quickly, and we went back telling, okay, we have a functional thing working. Let's see if it captures data without much of analysis of the field of medical or speech language pathology. So this dysphagia is being diagnosed usually by speech language pathologists. So we went back to them and we said, okay, fine, this is what we have. Do you think this looks close to what you guys wanted? I'm sorry, I was not presenting. Okay, so this is what we went back with. And the first time we went back and we tried collecting the data, that is when we got to know that engineering kept aside, be it electronics product design or electronic product design plus the other field, be it mechanical design or other things like picking the right material for getting the electronics working as per the domain that you're building for. In our case, it was medical device. The familiarity of knowing that domain and the potential challenges becomes a key factor to pick the right component and the right materials so that it works as at ease. So when we started building from that previous device which I showed, which was the initial prototype, and we went back to collect data uh, in the hospital, this is what we had. So it had an accelerometer and a mic. If you see, there are two graphs that we have tried plotting to just explain this. So one mic and one accelerometer, which is constantly capturing the data of the swallow, sound and the movement, and is also visualizing over a web-based application, and is also running a model with the data that we had collected data from these patients from various places in the hospital and old age homes, where the model which is able to classify, is it a swallow which is dysphasic or a safe swallow or a normal swallow, is what it was trying to run. Now, when we went with the working device, is when we realized that placement of this device to collect the exact required data of a swallow is something that we had not anticipated for, because that was not something known to the engineering world, right? So it is something specific to that domain. So that is when we had to come back again, iterate, change the casing so that it the fits the area of the neck on an average. So another parameter I would say that we didn't anticipate in the early days was the neck size and the neck girth of each person is different. And then on an average, sometimes we have had challenges of mounting this device around necks which had like roughly not more than 2 centimeter of neck size to mount the device, or sometimes the neck would be too long and we would not exactly know where to position this device. So both ways, both the challenges we had to navigate through by reading through a little bit of anatomy and understanding, and doing more of talking with the doctors to understand anatomy and ask them to recommend us the location and do more data collection to see where the data is more prominent, is what we had gone through. Then finally, even though functionally the device works, uh, the device, when it goes to an electronic device or an engineering device or an engineering product, or we can say an engineering uh, project result, when it goes to the hands of another person from another domain, their expectation and the way they handle it are also things that I feel is needed to be known to a designer of electronics even way before even the components are picked or even the design is made. So in our case, what we had finally gone back with a better working module after understanding the challenges of placement of the sensor on the neck and the girth and the kind of material that has to be used in the casing part of it. This is how it looked. So end of the day, we had like one device having three different colors of indicator, each one of which indicated a particular mode of the device, where the first time it is yellow and where it will collect, the device is powered on and it is setting up for collection of the data, and then it would turn to green, indicating that it is now ready for collection of the data and the person will be asked to swallow the liquid. And then the third mode was where the data would be sent over a BLE or a Wi-Fi, whichever is the preferred option chosen by the user, to a web-based app where we plotted the data as well as gave a spectrogram representation of the sound and the movement that we captured after a swallow data being captured. So let me know. I'll just quickly run through the video of our entire systems working. So this is just a screen capture of what we had finally. If you see the previous image that I showed, where the device entirely was a belt-like structure, and finally when we had to go back and validate it across the video fluoroscopy, uh, we had to again iterate and change another design, because the challenge again that was encountered was the video fluoroscopy against which we had to validate in the hospital had X-rays passing through the area of the neck, and the electronics that would be involved, majorly the processor block or the processor chip, would malfunction or would just give accident or garbage values once passed through the X-ray. So that was another thing that we couldn't anticipate, and had to change the device in order to validate. So this is what is the video that I have. Let me quickly run through it. So basically, we would just click on get data and then remotely initialize the collection of data in the device. And once the indicator is in blue, it would transfer the data to the web, and then we would visualize and then take it for further analysis, clean it, and then store it in the database. I think it was stopped for a while. So yeah, this is basically showing what uh, what all data of the patient or the normal person being collected is being loaded with the attributes related to it, and then we just save that data. So this is the device that we built as for a different field, for a medical field that we start building for. Now, this story being told of our own product development, I would say the ideal thing that we thought when we started, and then try to maybe engineering wise or electronically see what was the challenge that we faced. So the first part of our process, where when we started the phase one, was choosing an optimal processor capable of collecting data of these two sensors parallelly, simultaneously, at around 1 kilohertz of one sensor and 2 kilohertz of the other sensor, and parallelly storing it in the device, as well as sending it after storing into the cloud or to another host device. And after that, also be capable of giving a running a classifier on this device, because one part of the device was also kept, supposed to run a model after we have sufficient data, and give us a objective result telling yes, this swallow data is safe or risky. And after the first phase, the sensor selection and the compactness that we were looking for is what was the major phase for us. And since the electronics world doesn't have specific sensor for something anatomically challenging, or something made specifically for swallowing, we have to find the right fit for capturing the data at a distance which is something like a device wrapped around the neck is what we see, right? So at that distance, maybe less than a millimeter or a couple of millimeters, without adding noise. That is what. So off-the-shelf sensors worked well to begin with, but later on, things like sampling rate being high and simultaneously accessing it became a challenge. And we had to go through either, I think we tried 2 to 3 different processors to see how we can achieve this parallelly, simultaneous access, as well as running an ML model, which is giving us some classification results. And other than that, after the electronics was working functionally, the challenge was how to encase it with the right material, because whenever, if it is just another product which has to be enclosed into a weatherproof casing and brought into working domain, if it is a non-medical application, the challenges are less. But when it comes to medical application, let's say if it is a sensor based device or any kind of device that would sit on a body of a person and measure some parameters, the comfort and the safety of the patient also is of great value of thought that we'll have to give in the initial days. And that is when we would have constant conversation and try different material. That is where Stella had helped us iterate our different materials, our designs to even make it more aesthetically better looking, as well as safe to even wrap around. Sometimes small things like in terms of design, we would not uh, we would see it as an engineer, not as a uh, product that is going to be wrapped around our neck first. But when we finished one round of collection is when the feedback told us that it is tricky and should have more safer or comfortable designs. So that was second thing that we had to spend enough time going back and forth at the hospital to deliver a better experience even during the data collection of our device. And after that, the challenge was more of optimizing the model to run it back on our device. So the three categories I would say of major challenges that we now, when we sit back and look as an engineering team, is could have been reduced is if we had sat with doctors and had better inputs taken from the medical world, it would reduce the engineering life cycle or the developmental time by a great time with a very great numbers, I guess. Uh, but when we start innovating or building for a new field or an interdisciplinary field, sometimes we don't find the counterpart from the other field who can also convey it in the right way. So it is also important. Let's say we are building for another field. The other person who's telling us will have to be in a position to cross question and get the right requirement before we pick components. Else we would end up doing multiple iterations till we actually close the requirements to be functionally working as well as aesthetically working for the requirement. So overall, I would say whenever we try building or even before building, we should have enough interaction with the other world person whom the device is getting built for, and then think of starting design and development. So this is about my presentation. Over to you, Sumant.
Yeah, thank you, Mahesh, for the presentation. Uh, the whole purpose of conducting the webinar was to give some perspectives for somebody who is starting with a hardware product development, and also for somebody who don't have any technical knowledge, who is not from a engineering background. Probably he's from, not from electronics background, or not from an engineering background at all. Like a doctor, in your case, you had also a doctor in your team.
Hmm.
For such person, what if we can give some clarity or some information which will help him to plan the product, plan the development, and get some clarity. If I want to build a hardware product, this will be the challenges. If there is electronics in it, I have to look for people with this kind of skills, or this kind of these are the steps which I might have to go through. If such information can be given, that will be helpful. So that was the purpose behind the uh, webinar, and also to cover or give exposure with respect to building a POC, MVP, and the challenges in going through the production, or at least low quantity production. So I have a couple of questions, and also if anybody have the questions, they can also ask. Please feel free to ask. Uh, in the medical device you built, what was the overall role of electronics in that? How much percentage of electronics was there? Then how much percentage of software development was there? And how much time was spent on testing it and reiterating it?
So majority of the overall system, if you see, there is nothing which doesn't run without the hardware, or I can say 60% or 60 to 70% of the entire system was electronics, and maybe 20% of the effort would have gone to building the rudimentary software which we had to visualize the data enough before it is getting stored. And rest of it, I would say, is the coordination, or how can I say, the 20% extra thing was the ML building that has to go and sit in the device. And answering your question about testing, so testing, I think the majority of the effort has gone into testing. At least if I say out of 100% of the time from starting building a device, at any given point of time, you would be testing it in the lab, then immediately going to the hospital, testing it there, and come back with challenges and rework. So I would say, once the idea was clear, this is what we wanted functionally, within a month, the device would be ready. And the next 1.5, 2 months would be about collecting, coming back with new challenges and minor changes and back. So over a period of 1.5 years, I think at least 7 to 8 months was hospital data collection mode.
The rest of the 10 months which you told,
Mhm.
was it majorly spent on the hardware product development, or what was it majorly spent on?
The initial 10 months had to be more the engineering, development, and testing of the sensors, selection of the sensors, and finalizing of the sensors. So we can say just the engineering or the electronics part of it. But once the first working MVP was ready, or the working device was ready, after that we have less time to spend on engineering and more time to take feedback with the working device.
Uh, so another thing is with electronic product development, there are so many tools out there, and especially with the open source, they have a
Correct.
lot of tools out there and a lot of libraries out there, sensors out there, which can be
Correct.
used to at least come up with the POC immediately.
Correct.
Then to go for building a MVP, where which have, in your case, medical device, you have to test it with the doctors, test it with the patients in hospitals.
Correct.
Then the compliances, etc., will come into picture, and you have to go a bit deeper at component level.
Correct.
So if you can shed a little more light on what on the tools you used while building POC, and how open source has helped, or what are the information sources online which people can at least refer to while planning their product development.
Okay. I think your question was more like, if I got an idea to begin with, what can come handy to, at least for myself to do, and then approach to another company or a developer who can do it full fledged, right? Like something to get started with, right, Suman?
Yeah, something to build a POC to
Okay.
quickly. Yeah.
So I think things like in the embedded world, at least things like Raspberry Pi, Arduino, and ESP32 are the boards that are capable of rapid prototyping. And these days, a lot of other more compact boards with powerful processors, like Seed Studios, Seed is SEED, are coming up with a lot of. They have their own portfolio of development boards. So picking up a development board like all either of these which I mentioned, and getting it basically working is easy and doable for anybody who is not even from the engineering world, because there is enough community and enough code base or any libraries. Even if you don't understand how it works, you can get it working. But the challenge there is, since you got it working, sometimes it feels like, oh, this is all building for the functionality to work, or putting your idea to just get it working, and building it at a precision and at the reliability level at which a product or an MVP which should reliably, continuously, consistently work, is a different thing. So I would say Arduino, Raspberry Pi, and DSP and Seed Studio, or any development board that, let's say you identified some kind of processor which has a capability to perform or deliver your design's requirement. Let's say you have some AI ML or ML algorithm or ML model to run on a particular processor which needs a particular hardware architecturally supported on the processor to run on it. So these days, if your requirement is that clear, uh, uh, if your requirement is that clear, we will be you will find enough development boards from specific companies. Like even we have tried buying boards, development boards from companies like ST, NRF, NXP, to actually evaluate if whatever the capability that we needed to run the embedded ML was actually the case of what they are portraying. So a lot of times we have done that as well.
Okay.
I'll
Uh,
try to drop some links, Sumant, maybe by the end of this
yeah,
conversation, so
yeah.
that it can help any of the participants here.
I also feel there are so many sources out there. Even if you spend enough time on GitHub or Hackaday, Hackster, etc., or even on Instructables,
Mhm.
something related to the few parts of our devices or our ideas might be already implemented there, and that also can help us to at least gauge the scope and at least
Correct.
get a confidence that this can be done. But these are the things which are to be needed, and these are the skills which are needed, etc. And from
I think
POC,
I think we have a question here, Sumant. So the question says, how did you design the PCB? Where did you get the PCB fabricated? So in our case, our team itself was capable of designing the PCB. I mean, the Gerber file of it. We would make schematics and make the layout and generate Gerber files. And in our case, we tried multiple vendors to get the right quality of PCB. So we have tried JLC PCB, Power PCB, all these online PCB manufacturers who say that they deliver on time, but we have had challenging times where we had to wait just because we had to wait to go to the hospital just because the PCB has not arrived for our next iteration with the improved hardware as per the previous iterations feedback. So uh, we also tried some local vendors who would fabricate the PCB. So we have tried all online mode of JLC PCB, Power PCB, as well as local vendors from Bangalore. Uh, but identifying a vendor who gives you quality PCB is also another thing that we took some time to finalize, because only once you see their quality of PCB is when you realize.
what worked for you, the online vendors or the local vendors from Bangalore?
I would say the local vendors from Bangalore in terms of delivering on time, but the quality was still better in the online mode of all these platform-based PCB vendors like Power PCB. The quality was good there, but the overhead and the lead time would be unpredictable. And sometimes even tracing where the order is was a challenge.
Okay. And so also another aspect is development tools required for building. You would need the software to code, the software to design the PCB, and all those things. There are professional tools or the tools, licensed tools, and also open source tools, which came more handy in your case.
So for a couple of designs where we specifically used boards which had companies like NXP or ST have their own IDs, and they would have their full version of their IDs for a price for a license fee. But most of their developer version was sufficient enough for the requirement that we were building for. And the challenge there is every IDE is a non-standard IDE compared to any tool if you would pick up. No software from an engineering company or a chip maker company will be, like a UI friendly or user friendly approach like how Arduino. You have two buttons and you just click and compile and upload. No. So the learning curve for if you're picking a more capable hardware for which the IDE is coming from the same company, let's say LXP, ST, or NRF. The overhead also would be to learn that particular IDE, and it pays off ultimately because you are trying to. Uh, One thing that I have realized as a team when we tried building and using the IDE that came from the same company. The chip, let's say we picked an XP and we used an XP's IDE, then we were able to design better or more efficient code because the compiler also would be designed for, and there would be libraries supportive to get started. And learning curve was the challenge there. But otherwise, things like platform IO, where it's an in-between world between Arduino and the software that gets shipped from the companies, where you get like a visual code kind of experience, but you can also leverage the libraries that are coming from Arduino.
Okay. Uh, we have another question. How
Yeah.
did you make microphone not pick the ambient noise? It's more related to the sensor and calibrating the sensor. If you
Correct.
can
Well, this
cover
is
the
a
microphone
good question.
aspect and also the sensor and calibrating the sensor aspect as well, it will be good.
Correct. So the very first few iterations of our microphone, uh, our initial work was just to get an interface. That is when we realized that the kind of sound it would create when it would rub against the skin in the swallowing process, all that would get picked. So after that, we had to write our own noise cancellation code and clean the data even before it got stored in the firmware itself. So we had implemented some kind of filters that became part of the firmware.
These filters were software filters only, is it?
Yes, yes, yes. We had
It were,
enough references for building a noise cancellation firmware, and that should be good enough until and unless you're doing something very specific where you'll have to use some kind of DSP kind of coding that you really need in your application, say trying to analyze some kind of music, and you need real good different capabilities in terms of hardware.
mm,
That is when you would probably have to understand that part of the hardware and write firmware for using that particular DSP block or filters that are very specific.
okay. We also have another question. What was the BOM cost? Uh, this is a very good question. Also, if you can please shed light on what is BOM, uh,
Uh-huh.
what is BOM, and what was the BOM cost of your product, and how did you plan the BOM? You can explain a
So
bit.
in our case, the bomb was we didn't have a what do you say hard stop for bomb, but we would when we did component selection, we would always weigh the option against at least two to three parameters, one of which would be cost. So our device, when we started building, the competitor device was around 2 lakh rupees, which was what we wanted to beat by building a device like this. And our proposition was we'll sell at least 4 to 5 times lesser the price. And if we'll have to make revenue, then we'll have to be able to manufacture it at a lesser price than what we'll have to sell it at. So our BOM cost, I think, including all the mechanical design and the casing and all, came up to 10K or lesser.
I,
So
you,
majority of the price, yeah, yeah, yes, sir.
so you went reverse way, comparing with the competitor device. You went the
Correct.
reverse way, or you planned from
Correct.
the.
So, we had a reference price against which we would have to make it lesser than that to, you know, talk the story of price being less in our device, delivering a similar or a better functionality. And that number for us was 50,000 to sell. So it should be made for a lesser price more than that. I mean, less than that, right? So we had kept a cap of around 10,000, and pretty much we managed to get that less than 10,000. I think we were around eight and a half K or somewhere there. And the biggest cost there was of the processor. And if you consider electronics, and the other part which was costly was the material that went into the casing of that device. So that is what was inevitable for us, because we had to pick biosafe material, and each ml of that biosafe material was around 200-300 rupees. So the costliest item, if you ask me, on that belt, which had glowing lights that you saw in the PPT, was the casing, not even the electronics.
Okay. I mean, the final cost of the device will also depend on the, um, there will be overheads, the
Correct.
operation cost, etc., and also the compliances and testing cost will add to it. Mm.
Correct. If it is the
Uh,
medical world, there is more money to burn beyond the engineering development, which is the hard reality, because the in the medical world, the product life cycle is defined like that. Even before you reach the market, there is at least two to three different regulatory or clinical trials or preclinical trials and compliances. Uh, Innovator or a project or a device has to go through, as a device, as a company, as the process that is. Uh, I don't know how familiar the crowd is with things like ISO standards, specifically for quality management system and medical device, which may be scary to start with. But if somebody is building for the medical world, the sooner you're familiar with the challenges or the pathway that you'll have to take, it's better.
yeah. Also, Niranjan sir has asked about how did you power the device? Uh,
Okay.
also, your answer will follow up with another question.
Got it. So our hardware that we designed had its own power management system. So it had a PMIC for connecting a lithium polymer battery, which was also enclosed in that build, and with almost 2 hours of backup of lithium-ion battery, around 500 mAh of LiPo, and it would go on for 2 hours with a full charge.
Okay. Um, uh, when we say electronic product development or a embedded system,
Mhm.
uh, the processor, sensor, how do you power it, the storage, and the communication channels. These are the
Right.
broadly the parts of the an embedded system.
Correct.
And from POC, at the stage of POC, you can pull in any product development boards or whatever is handy and try implementing it. Then once you go to MVP, or where you want to actually test on the ground, the compliances, the accuracy, and all those things will come into picture. And once you
Right.
go for manufacturing, planning the bomb comes into picture. And at
Right.
that point of time, even the smallest costs also can affect sometimes. Either these cost aspects come into picture either due to the limited funds the team has, or if you are going to the market, it's the amount of cost which has to be spent on the to reach the customer, and the amount of spend which has to be spent to reach the customer also includes the compliances and testing, the marketing, and all those things. So now, when you went from how much had you spent on choosing the right hardware devices, or and planning the bomb. And have you uh, like the in terms of powering the device, in terms of choosing the storage and choosing the processor,
Mm.
uh, when did this became critical in your development process?
Mm. It was critical in the early stages itself because our
And
engineering requirement.
uh, majority of the components which are used, which are required in any device, are widely available. It only becomes critical when the accuracies and technicalities and whatever you want to achieve is not achieving, or the cost becomes a factor, or complaints becomes.
Two things. Okay, I would answer this in two folds maybe. So one is, let's say you want to just get it working, and then you continue building it, and let's say when you got into a stage where it worked enough and you validated enough and you want to scale it up and build it in more numbers. If that is when you hit a hurdle of not able to debug or not able to manufacture at a lower cost, because that enabled you to get it working till MVP. But beyond that, it is costly. If the chip, when you buy at big numbers, are costly, and you have not taken that route because your IDs were supportive and your community support was good, you will seriously regret taking that when you realize that there were more powerful hardware and more powerful chips for cheaper rate. And after a year of development and validation, if you hit that place, you're losing time. So after a year, you'll have to again go back to picking up a processor, which will reduce your BOM and increase your revenue, uh, or increase your profit margin by reducing the BOM. If that thought process is not clear, or I would say if your engineering requirement is not clear or specific, let's say I just want to get it working, one, and second would be an engineering requirement which says I want to get it working at this sampling rate, and I want a result of classification at this particular accuracy no matter what. So that is when you would be a better judge of trying maybe multiple processors or multiple components in the early stage and burn more at that stage, rather than redoing the development because you made a mistake of choosing the easier and a faster path in the early development. So I would say we spent a good amount of time. We have burnt more money in the early stage where we tried out and rejected multiple processors and multiple development boards because it didn't match our engineering requirement, which said it will have to be capable of collecting two sensors data simultaneously at a given sampling rate of 1 kilohertz and 2 kilohertz. So we rejected, but finally, when we boiled down to one board, it paid off.
Yeah. Divakar has asked, what was the role of TinyML and what data was used to train the model?
Okay, so in our case, the data that we had collected itself was used to train the model, and the role of TinyML here was using a framework, or using the framework. Point one. Point two is also optimizing the firmware to run on a microcontroller or a processor-based hardware. So that is what TinyML enabled us to. You
I
can
also
answer.
like to mm, highlight a bit on the open source tools which are widely available. I think you had used KiCad for designing the PCB, etc.
Oh, correct, correct.
So in terms of development, there are wide range of tools out there, and mm, in terms of getting the knowledge, uh, if you can refer few sources, like what forums would you go to find answers for your solutions, answers for the problems which you are facing, uh, or what sources would you go to quickly find components? If there are any websites or platforms, uh, if you can share, it would be probably helpful for everybody, because we'll also be putting
So
this online.
got it. So I think if you are looking for components, the websites or the kind of component that you would need is scattered all over the place. At least if you want something very quick and you are not worried about the money, I think Robo.in is having a lot of off-the-shelf components, more generic ones. But if say your components are very specific, then you will end up finding something in DigiKey and other places and ordering. That overhead is still there if it is a very specific specialized sensor. But otherwise, Robo.in and uh, is what we have not had a delay time in terms of Robo.in for any embedded components as such.
Okay.
And if you're looking for any kind of resources and you're trying to get, uh, you know, yeah, if you're looking at data sets and you're trying to see, try to build tiny ML models and run it on, processor based hardware, I think Kaggle, if people are not familiar, is one place where you get data from all walks of life, I would say. Uh, but disclaimer, you'll have to understand the source and the way they have collected the data first before using it in your use case. A lot of times it would feel the same, but you'll have to scrutinize before using somebody else's data. So, and the best way to get your own data is to collect it yourself. That is why we had taken the path of building our own hardware, collecting, and then building a model with the data that we ourselves, generated.
Yeah, there's also another platform I think called Find Chips, which will also help you to suggest and also find price comparison of different components as well. Uh, there are
Correct.
so many platforms out there, uh, and whether it is uh, building the embedded system using building a device using Arduino or Raspberry Pi, building the PCB using EasyEDA or Altium or KiCad, or building the enclosure for it using Fusion 360 or Tinkercad, or finding an enclosure on Thingiverse. There are so many platforms out there. Uh, the clarity on product development, clarity on the requirement, the domain knowledge, and at least development path will help. At Stelna Designs, we started this webinar to at least try sharing our uh, learnings and also learn from the ones who participate. And we are also building a platform where we are creating a tool using which you can easily create enclosures, mechanical components, and eventually plan some aspects of product development online itself. You can generate the CAD models and get price comparison, etc. online. I would request all the participants to have a look at it as well. And at Tiny Prism, Mahesh and his team are building their own devices and also providing services. Before closing, if you want to share a little bit on what you guys are doing apart from the medical device, you can.
Sure. So basically, we help other founders or other thinkers uh, take their load of unfamiliarity and convert their ideas into embedded solutions. So, say you have some idea, we would sit with you, run you through the requirement phase, and boil it down to an engineering requirement and build a custom hardware for you.
Yeah. I think with this we can close the webinar. Uh, okay, Mahesh, I thank you for all the knowledge shared and being patient with answering all the questions. I also thank all the participants for staying through the webinar. Thank you so much. Have a good day. We'll close the webinar. Thank you.
Yeah. Thanks, Sumanth, for the opportunity.